right, continuing with the atom, we're going to be talking today about the structure of the atom, the subatomic particles and the nuclear atom. We're going to be doing a little bit of backtracking, talking about what you already went over with history a little bit, and I'll hopefully be able to explain some of their experiments a little bit more. Okay, so the atomic models. Atomic models represent the best understanding of the atom based on the observations and inferences of the time. So the atomic theory that we talked about, they had models for that based on what they knew back then. The discovering the electron, if you remember, the experiment that was done. Okay, if you remember the experiment that was done with the cathode ray tube, all right, this is an example of that. And at the time, the recently invented vacuum pump allowed the scientists to understand electricity in the absence of matter. So tubes were with nearly all the matter or the air taken out of them would have electricity pass through them. So you take this vacuum tube, you take all the air out. They filled it with certain gases, but they filled it only with that gas so that they would know what kind of atoms were in it. Then they stuck the cathode, the negative energy particles on one side, and the anode, the positive, on the other, hooked it up to a battery, and then tested to see what would happen. So the two metal terminals are attached to either side. Like I said, the negative for the cathode, the positive for the anode, and then let the electricity pass through it. One day while working in his darkened lab, an English physicist saw a flash of light within one tube. It was some form of radiation hitting the end of the tube, which had been coated with light-producing materials. Because the material that was striking the other material was from the cathode, it became known as a cathode ray tube. It just as easily could have been known as an anode ray tube, but we call it a cathode ray tube. So because the material was coming from the cathode side, so it was coming from the negative side, we know that those are negative particles. Okay, this was all work done by Sir William Crookes. So I don't know if any of you have an idea what this is. This is actually a pretty good use for a cathode ray tube. It's actually an old television. And this we're looking at it from above, okay? So here would be the screen, okay? This whole part right here is actually what shows out onto the screen. So this is the cathode ray tube in this area. So I don't know if you've ever seen a TV like that, but that's what they used to look like. All right, so by the end of the 1800s, they were convinced that, one, cathode rays were actually a stream of charged particles, because here in this experiment, if you took a magnet and put it here, you could actually bend that light, that ray that was coming out. And number two, they were also convinced that particles had a negative charge, though they could not calculate the exact charge. But the fact that they could say they're negative was pretty impressive. So if you look here, they have a positive magnet on this side. So as the beam is coming out, if it's attracted to the positive side, that means it has a negative charge. All right, so scientists replaced the tube with different gases, and no matter which one they used, the properties are always the same. So this showed that matter contains the elements being looked at, and two, that negatively charged particles is what they saw, and now we call those electrons. All right, so how big is an electron? There was no way for them to calculate it when they first discovered that they existed. J.J. Thomson, who lived between 1856 and 1940, began a series of detailed experiments to determine the charge to mass ratio. So depending on how charged it was, did that determine the mass? Or how was that? What was the ratio to the mass? So he carefully measured magnetic and electric field effects on the path of the ray, and he concluded that the mass of the charged particles was lighter than the lightest known atom. So this was pretty shocking because they thought that the atom was the smallest thing out there still. So this meant that the atoms were divisible, and Dalton's theory, part of Dalton's theory, was incorrect. So next we bring up Robert Millikan, and he was an American physicist who determined the charge of an electron. So we know it's negative, but how negative? So knowing the charge of an electron and knowing the charge to mass ratio, he calculated the mass of the electron. So even though it was almost 100 years ago, his experiment setup and what he could do in the lab and the calculations that he did are actually within 1% of today's accepted value. So that's some pretty good science and some pretty good math going on. This is the setup that he did in order to figure out that calculation, and it's pretty complicated. All right, since then we have gotten rid of that number for the electric charge, and really we just have equated it to a single unit value, and we say that an electron is -1. So it's much easier than having to work with that number that they came up with. Okay, the mass of an electron is 9.1 times 10 to the -28 grams. Okay, so this is equal to 1/1840th of the mass of hydrogen. And remember, hydrogen is the lightest element that we know of. So the lightest element we know of is still 1,840 times bigger than the size of an electron. So when we talked about the atom, we said it's really small. Well, this is even really, really smaller. Okay, no, that's not good grammar, but it's small. Okay. So we have all this new information, and we know in science that new information always leads us to having new questions, more questions. All right, so more questions. If electrons are negative and all matter is neutral, and you know all things are neutral because when you touch something you don't typically get shocked, what evens out the negative charge? So we have a negative charge, what makes it neutral? And if the mass of an electron is so small, what accounts for the rest of the mass of the atom? Okay, you remember this model that J.J. Thomson came up with? It was called the plum pudding model, or the chocolate chip cookie, or the chocolate chip cookie dough model, whatever it's called. This idea that you had matter containing evenly distributed positive charges, so kind of the goo throughout at the cookie dough part, and then you had the electrons just dotting throughout the chocolate chip part. Okay, remember that theory? Okay, and then Rutherford, who was actually a physicist, which, and if you've been paying attention, a lot of these guys have been physicists. Okay. Rutherford was also, and he actually was a pretty pompous physicist, as they can be, and he said all science is either physics or stamp collecting. So as you can tell, he gave a lot of credence to the other sciences. All right, but what's funny about that, the irony that we can have, is that in 1908 he won the Nobel Prize, not in physics but in chemistry. So you know, I'm sure he didn't turn down the Nobel Prize, even though it was in something he saw as menial as stamp collecting. But he lived during a time when physics and chemistry were compatible. They had not diverged in their subject matter as much as they have today. So a lot of what we're going to be studying in this chapter will just really be conceptual physics. Okay, so you can tell your parents that you're studying conceptual physics this week. All right, so Rutherford was extremely brilliant, and he was willing to work longer and harder. I'm sorry, he was not extremely brilliant, but he worked really hard and worked really long, and he figured out the answers to quite a few problems. Okay, He moved to Cambridge and then to McGill University in Montreal and then to Manchester, where he did his gold foil experiment. If you remember anything about this experiment from your reading, but what he did is he shot a beam of alpha particles at a thin sheet of gold foil. Around the gold foil, he had a zinc sulfide sheet. And so what he did, that's this zinc sulfide screen is here, okay? So he shot alpha particles out from the gold screen up to the gold foil, and what he was doing was he was tracking where the beam happened to go. Did it hit something, or was it able to go all the way through? Okay, so it's been 100 years since he discovered this atomic nucleus, remember, because the beams shot off. So here's a quick video that will just show you, someone's going to actually do the real experiment, okay?
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing and what we're doing here is taking a beam of particles, firing at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behaviour of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometres in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom, by comparison, is very big. So it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
Okay, so the nucleus is really small, okay, but do you understand the experiment and what he was able to prove from that? Okay, all right, so how much space? Okay, if the atom was the size of 2 football fields, the nucleus would be the size of a nickel. Okay, so not just 1 football field, 2 football fields put together, the nucleus is only the size of a nickel. All right, so again, we're talking about really small things for this whole chapter. All right, so discovering the protons and the neutrons, which make up the nucleus. So the mass of an atom was still unaccounted for. We know there's electrons out there, but they're so tiny that doesn't really give us where does the weight come from that's in an atom. So Rutherford finally refined his model to include protons as the positively charged particles in the nucleus. The proton is also a subatomic particle, but it carries an atomic charge of +1, which negates the electron's -1. One of Rutherford's co-workers, James Chadwick, showed that the nucleus also contains subatomic particles, which are called neutrons. So Rutherford came up with the protons and the fact that there was a nucleus there. Then his colleague found the neutrons, which are the neutral, they don't have a charge, the neutral particles. Okay, so this particle has nearly the same mass as that of a proton, but has no electrical charge. And together the 3 subatomic particles account for all the mass of the atom. So if you see that the electron is negative, and it has a negative charge and has a relative mass of 1,840th. The actual mass, 9 times 10 to the -8. The proton, positive 1, a relative mass of 1, an actual mass of 1.673 times 10 to the -24th, and a neutron, which has no charge, a relative mass of 1, and an actual mass of 1.675 times 10 to the -24th. So the protons and the neutrons have almost the same actual mass, but are considerably larger, 10 to the -4th difference between the protons and neutrons and the electron. All right. The atom. Atoms are neutrally charged due to the protons, neutrons, and electrons. They have the same number of protons and the same number of electrons to even that out. Atoms are spherically shaped with a tiny, dense positive nucleus and fast-moving negative electrons. So the protons and the neutrons are together in the nucleus of the atom, and then the electron cloud around the outside. Electrons are held within the atom by their attraction to the positive nucleus, and the nucleus makes up 99.97% of the weight of the atom. So the electrons stay where they are because they are positively attracted to the nucleus. So we've seen that 1, elements can be broken down into atoms. 2, the atoms can be broken down into subatomic particles. So, question now, can subatomic particles be broken down into smaller particles? Because remember, in science, once we find something out, we don't stop there. That then leads us to having more and more questions. Okay? So, the answer to this question, can subatomic particles be broken down into smaller particles, is yes. So, let's talk about quarks.
What are quarks? Over the past century, discoveries in physics have come thick and fast. Some have changed the way that we understand the world. An understanding of the structure of the atom has been a huge focus of scientific research, and it has heralded an era of discovery unlike any we have ever seen before. In 1964, Murray Gell-Mann and George Zweig suggested that most of the known particles of the time could be explained as being combinations of three fundamental particles. Now, the term fundamental means that the particle does not have a substructure. It cannot be split. The name quarks was chosen from the James Joyce novel Finnegan's Wake. 3 quarks for Muster Mark. In order for their calculations to work, however, these quarks needed to have a fractional charge. This was a new concept, as fractional charges had never been seen before. Quarks are the fundamental building blocks of all particles that we know of. At the Stanford Linear Accelerator, electrons were fired at protons and found to bounce off of tiny particles inside them. It had taken 4 years, but this was the first evidence for the existence of quarks. At the time, there were 2 basic quarks. The up quark, which has a charge of plus 2/3 of the charge of an electron, and the down quark, which has a charge of minus 1/3. How are they different? They all have different masses, as well as charge, and another property called spin. The up and the down quarks are the most common and least massive. The proton was found to be made of 2 up quarks and 1 down quark. Now, we know that the charge of a proton is +1. If we look at this in terms of the fractional charges given to quarks, 1 up quark would have a charge of plus 2/3, so therefore 2 up quarks would have an overall charge of plus 4/3. Adding in a down quark reduces the overall charge to 3/3, which is the equivalent of 1. A neutron was found to consist of 2 down quarks and 1 up quark, which gave it an overall charge of 0. The discovery of the up and the down quark was followed in the coming years by the strange quark, the charm quark, the top quark, and the bottom quark. Quarks have quite strange names. Up and down were named based on components of their spin. Strange quarks were given the name strange because they were observed in particle decays that had slightly longer lifetimes than they should have done. The charmed quark was given the name because of its fascination, the way that it fascinated the physicists at the time. Bottom and top quarks were chosen by a famous physicist called Harari. He chose the names because they were the logical counterparts of the up and down quark. Quarks are never seen on their own, and the evidence for their existence comes only from particle accelerators.
Okay, so we've seen 2 videos today that have both talked about the Hadron Collider in CERN in Switzerland, and hopefully we'll be able to talk a little bit more about the Hadron Collider. I'm hoping to have time to really explain to you guys what it is, and as best as I can explain what it does and the purpose for it. I'm not a physicist, and it's a lot of what happens with the particle accelerator is beyond me, but we'll try to get into it and maybe we can all learn a little bit more about it. All right, so make sure that you've taken notes on all of this. Make sure that you've read through the chapter and you're ready to come to class tomorrow. Have a good night.